At times, we used to put things together and assemble it with the help of a bolts and nuts, either at home or workplace or even at a garage. So in the process, we used to ensure that when the bolts are properly tightened and does not have any kind of loose contacts, such a way the components are rigidly held and does not fall apart. So in this video, I'm going to show you the influence of the bolts in tension or bolt pretension and why this bolt pretension have to be included in our CAE analysis to ensure the right behavior of the structure or to understand the right strength of the structure. This is a CAD model of a structure where we have two components. One is the column and one is the bracket. And the column is the one which is made of rectangular cross sections, which is a thickness of 2 millimeters. And the bracket is also a component which is having a thickness of 2 millimeters. And these two components have been assembled together with the help of bolts and nuts. And the bolts, what we have is a through bolt, such a way it passes throughout the width of the box sections so that it's going to be easy in the assembly process. We have created an FE model for this assembly in two configurations. The first configuration is we have created some kind of constraints at the bottom of the column in all degrees of freedom, such a way the column is going to be rigidly fixed. And we have applied force of 200 newtons at the top of the bracket, and 200 newtons is about 20 kgs. And these two components have been connected using the bolts of M6 size, so which is running throughout the section of this assembly, starting from this bracket through the rectangular sections. So in this first configurations, we have applied the K to the bolt, and the bolt does not have any kind of a tensions. It is just as it is, it's just fixed as it is. There is no tension in the bolt. So the second configuration is, it is the same as the first configuration. The difference is we have introduced some kind of a pretensions for the bolt, for the two bolt what we have. So the amount of pretension, we took it from the bolt data handbook. So we have about the clamping force, the maximum clamping force of an M6 bolt of class 8.8 is about 11.6 kilonewtons. And even though we have this 11.6 kilonewtons, generally we will not be in a position to tight till that point. So we have taken a new clamping force of up to 500 newtons, and that has been applied on each of the bolts. That is going to be the pretension for this in the second configurations. Apart from that, the constraints of the forces are the same in both the two configurations. We analyzed the two configurations of this assembly for its structural strength, and let me show you the comparisons of the results. The model, what you see in the left side, is the configuration 1, where we have the force of 200 newtons applied on the top of the bracket, and there is no tensions available in the bolt. The bolt is as it is. So we have only one loads in the first configuration, what is in the left side. Whereas on the right side, we have this load of 200 newtons applied on the top of the bracket. Plus, we also applied some kind of a pretension on the bolt in the axial directions. The pretensions are 500 newtons applied on each of the bolt. And let me show you the results of the displacement contour because of the pretension happening on the bolt. Yes, we can able to see the displacement contour. So we are able to see a maximum of 0.9, that's about 1 mm happening on the column. So where we can able to see the column, where the column is getting pulled in because the bolt, what we hear, because we applied some tension, we are trying to, whenever we are tightening the bolt using the nut, so the part is getting pulled inside. So we can show you some kind of a scale factor for a better understanding. We can able to see this part is getting pulled inside. So it's a high scale factor, but that is not the case. It is just only for visualization purpose. So the maximum pulling distance about, we can able to see maximum for close to 0.10, that is 1 mm we can say. 1 mm or inside displacement is happening because of tension happening on this model. And whereas if I see the stress distributions of this component because of the tension happening in the bolt, we can say about, yes, we can able to see the stress distributions happening through the column, at least the top portion of the column is getting distributed because of the bolt. So when the bolt is getting pulled in, we can able to see the stress. We are observing the stress of maximum about how much, about 200 megapascals. So we have used this is a general steel where we can have this steel of about 260 megapascals at the yield limit of this component. So we are experiencing a maximum of 200 megapascals only for the tension in the bolt. Whereas in this case, there is no tension because we are not seeing any kind of stress distributions. You can see only the animations here. There is no results for this one. So, but when we include the analysis for the other load also, because the load of first we are going to put this component together, tighten it. While tightening, we are able to see this kind of stress distributions of this component. And let me show the other load case as well, that is the load of other things. The moment if you, after tightening the bolt, when we apply the force of 200 newtons on the top of the bracket, we can able to see the stress distribution of 260 megapascals, which is absorbed on the bracket. And this is because of the two loads, because the two loads is because the one load is tension, pre-tensions on the bolt, and the other load is of the 200 newtons applied on top of the bracket. And here we have only one situations where the force is only one conditions where it's applied on top of the bracket. If we can see the difference between these two components, you can clearly see the model what you see in the right side, where we can able to see the realistic stress distributions because of the pre-tension applied on the bolt. Whereas in this case, even though the bolt is here, but we are not, because we have not applied any kind of a pre-tension on the bolt, the stress distribution is happening only on one face of the column, and which is not realistic, because in realistic we will be applying some kind of a pre-tension by tightening the nut. So what we can conclude from this analysis is, wherever possible, where there is, if I find any kind of a gap between the bolted components, so it is strongly recommended to include the pre-tensions on the bolts. So the model what we have in the right side, which is having the bolt pre-tension, is giving us more reliable results than the model which does not have the pre-tension. So it again depends upon the conditions of the model is, because the two parts are sandwiched together where there is no gap. This pre-tension may not have that much of impact because we have kind of a gap between these two components. The gap is the sectional of a box or the column having kind of a gap. Because of the gap, the part is getting pulled in. Because of that one, we are able to see some kind of stress distributions uniformly in this component. And now I think based upon these results, we can take a call whether this component is good to go for manufacture or for further processing. Of course, maybe if it is going to be one-time load, it's okay, but none of the component nowadays is not going to be one-time load. So we have to see this for endurance limit and also check for the fatigue limit also if it is required. I hope you understand the effect of a bolt pre-tensions and how it influences structure of assembly in terms of its stress distribution, also in terms of its displacements. If you want to know more about the different kinds of CAE analysis, or if you want to learn and become an expert in the product design using CAE simulations, you can visit us as www.skillmac.com.